Hi everyone, the topic for today is the differential. We're going to start by recalling the definition of the derivative. The derivative is the limit as delta x approaches 0 of delta y over delta x. If you remember, delta y is the change in the function, which is y2 minus y1, and delta x is the difference between x2 and xy. In other words, delta y is the change in the function and delta x is the change in the independent variable. But then we used some different notations. Some of them were that f prime of x equals the derivative of y with respect of x. Last semester, we didn't give a different meaning to this quotient. This semester, and the purpose of the differential is to show you the meaning of the differential of y and the differential of x, and that you know that the differential of y could be a good approximation of the change of the real change of the function when the differential of x is small enough. In this graph, we can see some of the definitions we saw in the previous one. First of all, we have x and an increase of x, which is delta x, that comes to x0 plus delta x. So delta x is the change in the independent variable, and you calculate this by doing x2 minus x1. Now look at the y-axis. We have this point that has coordinates x0, f of x0. And we have this point that has coordinates x0 plus delta x, f of x0 plus delta x, which is y2. So we have y1 and y2, x1 and x2. And the difference between this is delta x, and the difference between this y2 and y1 is delta y. Now, we have a function here that is drawn with blue color, and we have this straight green line, which is the tangent at this function at the point x0, f of x0. Do you remember that? You may remember that another interpretation of the derivative is the tangent line of a function at a certain point of this function. Now, in the next animation, you're going to see that when x2 gets closer and closer to x1, delta y becomes closer to the differential of y. And the difference between the real change, which is delta y, and the approximation, which is the differential of y, are pretty small. That's why we say that the differential of y is a good approximation of the real change whenever this change is pretty small. In this video, we're going to see how when the differential of x becomes close to 0, then this point gets closer to this one. And delta y, which is the difference between f of x2 minus f of x1, which is the real change, gets closer to the approximation of it which is the differential of y. So let's play the video. Well, let's play the video. Here you have the difference of x2 minus x1, and when x gets smaller, when x2 gets closer to x1, delta y is getting closer to the differential of y. As you can see here at the top of this difference, you see how when the differential of x comes close to 0, then the difference between the real change and the approximation, which is differential of x, gets smaller and smaller to almost 0. So that's why the differential of y is a good approximation of delta y. Look at this, look at the video. So the difference between x2 and x1 gets closer to 0, and the difference between the real change, which is delta y, and the differential of y is almost 0. You can see in this animation that in some problems we're going to use the differential of y as a good approximation of the real change, which is delta y. Okay, now it's time to solve an exercise to show you what we're meaning about the previous explanation. So we're going to work with this function, the function y equals 3x squared minus 4. We're going to start with x equals 2, and the differential of x is going to be 0.1. But I would like to point out that we are asked to calculate a few things. We are asked to calculate delta y, differential of y, real change, approximation of the change, and the difference between the real change and the approximation. So let's write the function up here. That function is y equals 3x squared minus 4. And we're going to work analytically, and we're going to calculate y1 with the first value of x, which is 2. So we have x1 equals 2. We have the function. You remember this notation, f of x1 means substituting x1, which is 2, in the function. So if we do 2 squared times 3, that's 4 times 3 equals 12 minus 4 equals 8. So y1 equals 8. I'm going to write the function up here again, not to forget what we're doing, 3x squared minus 4. But now we're going to do the calculations for the second value of x, x2, which is 2 plus 0.1, because the differential of x equals 0.1. So x2 equals 2.1. Then we're going to substitute that value in the function, 2.1, and we're going to do the calculation. So 2.1 squared equals 4.41 times 3 minus 4, and doing all the math, we obtain 9.3. Now, okay, so the value for y1 equals 8. And the value for y2 equals 9.23. If you remember the instructions, we were asked to find delta y, which is the real change in the function. We can do that by subtracting y2 minus y1, which is 9.23 minus 8. So the true change for the function is 1.23. This is the true change, which is actually delta y. Now that we have the true change of the function, we're going to use the differential in order to do the approximation and see how different is the approximation compared to the true change of the function. At the beginning of the video, we saw that we can write the differential of y equals the derivative of the function times the differential of x. And this differential of y is an approximation of the true change. So here we have the calculations for the example we have been working with. So the differential of the differential of y here equals the derivative of the function times the differential of x, which is the differential's definition. Now, the derivative of the function, if you remember, the function was y equals 3x squared minus 4. So the derivative of 3x squared minus 4 equals 6x. And we have that 6x over here, you can see it here, 6x times the differential of x. And if we substitute the values that we had at the beginning, which were x equals 2 and differential of x 0.1, we substitute in this formula and we obtain 6 times 2 times 0.1. And that calculation is pretty easy to obtain. It will be 12 times 0.1, which equals differential of y equals 1.2. And that will be the approximation using the definition of the differential. Finally, we're going to compare the real change with the estimated one. The real change is delta y equals 1.23. And the estimated value for the change of the function is the differential of y, and that value was 1.2. So now, the difference between the real change and the approximation would be 1.23 minus 1.2, and that equals 0.03. So, as you can see, if we use the differential, it's a pretty easier job compared to the job that we have to do by calculating the delta y. That's why we're going to use the differential of y to estimate some values for some function. Now you're going to do some practice. I'm going to give you 2 functions to work with. You're going to do the same calculations we did in this video. So look at the next examples. Take a sheet of paper and work with them. Well, now you're going to do 2 exercises. You're asked to calculate delta y, differential of y, and the difference between those 2 values. For exercise 1, you have y equals x squared plus x minus 1. You're going to start with x equals 1, and the differential of x equals equals 0.1. And the second exercise is going to be the function y equals 3x squared minus 3, and the value for x is going to be 2, and the differential of x is going to be 0.2. So take a sheet of paper and start working. Ask whenever you need it.